We're going to spend most of this semester solving linear systems of equations and linear systems of differential equations. So let's take a couple minutes now to see what linear systems of equations are, what linear systems of differential equations are, and what their solutions are. A linear system of equations looks something like a11x1 plus a12x2, etc., up to a1n xn equals b1. That's the first equation. And then a21 x1 plus a22 x2, etc., up to a2n xn equals b2. And let's say that, so we've got n variables here. Let's say there's m equations. Oh, sorry here. And the mth equation is am1 x1 plus am2 x2 up to amn xn equals bm. The shorthand for this linear system of equations is ax equals b, where A is the matrix of coefficients, x is a vector of variables, and b is the right-hand side numbers. Also, sometimes instead of ax equals b, we write just a b inside square brackets, and we call this an augmented matrix. A solution is a vector c1 up to cn such that x1 equals c1, x2 equals c2, etc., xn equals cn, satisfies the linear, let's say satisfies all equations in the linear system of equations. Now there might be one unique solution, there might be no solutions, or there might be many solutions. Let's do some examples of each of these possibilities. To start off with, let's let m and n both be 2. So the coefficient matrix is going to be a 2 by 2 matrix. So let's look at x1 plus 2x2 equals 2, and minus 3x1 plus x2 equals 1. And in shorthand, this is 1, 2, negative 3, 1, x1, x2 equals 2, 1, or just 1, 2, negative 3, 1, vertical bar 2, 1. In this case, there is exactly one solution. And that solution is 0, 1. That is x1 equals 0, x2 equals 1. It's natural for you to ask, how do we find this? And we're going to study that later, so don't worry about that now. But for now, let's just see that it is a solution. So if x1 is 0 and x2 equals 1, then we have 0 plus 2 times 1 on the left-hand side, and negative 3 times 0 again is 0 plus 1. And on the right-hand side, 2 and 1. We can see that these are equal. 0 plus 2 is 2, and 0 plus 1 is 1. And just to give you an idea of how I know that, how I got this, because in this case these equations are lines, and we can write these as x2 equals negative 1/2 x1 plus 1, and x2 equals 3x1 plus 1. And if you graph these, you'll see that there's one point of intersection, and it's precisely the point 0, 1. All right, let's look at another system of equations which has no solution. x1 minus x2 equals 6, negative 2x1 plus 2 x2 equals 4. Equivalently 1, negative 1, negative 2, 2, x1, x2 equals 6, 4, or 1, negative 1, negative 2, 2, vertical bar 6, 4. This has no solutions. Again, the natural question is, how would we realize it has no solutions? All right, don't worry about that right now. I just want to convince you it has no solutions. And maybe convince you it has no solutions. Now, the reason we can see this has no solutions is that the second equation is basically negative x1 plus x2, or I could rewrite it as x1 minus x2. If I divide everything by negative 2, we've got x1 minus x2 equals negative 2. Now if x1 minus x2 is 6, it's going to be kind of hard to make x1 minus x2 be negative 2 at the same time. There's no way we can choose values of x1 and x2 to satisfy both of those equations. So this has no solutions. Sometimes people say the system of equations is inconsistent if it has no solutions. All right, now let's look at a system of equations that has infinitely many solutions. I'm going to use x1 minus x2 equals 6 again, and negative 2x1 plus 2x2 equals negative 12. So let me just change this. So equivalently, the shorthand is going to be the same, except we have a negative 12 here and a negative 12 here. This has infinitely many solutions. Again, the natural question is, how would we decide that? Well, we're going to do that later. But let me show you how I know. So if someone tells you it has infinitely many solutions, you can check that by saying the second equation is, if we divide by negative 2 like we did last time, x1 minus x2 equals 6. So it's really the same as the first. It is a line, so everything on this line is going to satisfy the equation x1 minus x2 equals 6. And some of the points that it passes through are 6, 0. 6 minus 0 is 6. 7, 1, because 7 minus 1 is 6. 5, negative 1, because 5 minus negative 1 is 6. And of course we could find infinitely many points on the line. All right, now let's look at another system of equations that has derivatives in it. So the entries of the matrix are going to be functions of t, and the variables are going to be functions of t, and then their derivatives are going to be functions of t also. let me call this system of equations LSDE, linear system of differential equations. Well, first of all, let me define some functions. Let's let x1 be shorthand for x1 of t, and x2 be shorthand for x2 of t. Let's let these be functions of t. Then the linear system of differential equations is dx1 dt equals negative 1/5 x1 plus 1/20 x2 plus 12. And dx2 dt equals 1/5 x1 minus 1/5 x2. The shorthand for this is, so on the left hand side we can think of this as a vector d dt x1 x2, and then multiplying a vector of functions x1 x2 we have the matrix negative 1/5 1/20 1/5 negative 1/5. And then there's a 12 in there that's not multiplying x1 or derivative of x1 or x2. So I'm going to add this vector of constants, 12, 0. So we have the derivative vector. We've got a matrix of coefficients of the functions x1 and x2. We've got the functions, and then we've got expressions, numbers here. Possibly they could contain t, but I didn't put any t's in here. So possibly in t with no x1 and x2. And these coefficients of the functions x1 and x2 also could possibly contain t. So the expressions here could possibly contain t, and the coefficients of x1 and x2 could possibly contain t. Now, a solution to a linear system of differential equations is a little bit more complicated. We need to find functions x1 and x2, so basically this vector, so that these functions x1 and x2 and their derivatives satisfy all the equations in the linear system of differential equations. We've got derivatives and functions. Altogether they have to satisfy the equations. We have to find this vector of functions such that f of t, f prime of t, g of t, g prime of t satisfy all equations in the linear system of differential equations. This linear system of differential equations. All right. right, I'm going to leave that there because I want to give you a solution. I want to be able to verify that it's a solution. So one solution, turns out there are many. Again, it's natural to ask how, but we're going to do that much later in the course. So one solution is x1 equals e to the negative t over 10 plus 80, and x2 equals 2e to the negative t over 10 plus 80. Let me write their derivatives over here because we're going to need the derivatives too. So dx1 dt is negative 1/10 e to the negative t over 10. The plus 80 just disappears because when we take the derivative of a constant, it's 0. dx2 dt is negative 2/10. So I guess I can write that as negative 1/5 e to the negative t over 10. Alright, so we need to make sure that these functions and their derivatives satisfy all of the equations in the linear system of differential equations. So the left-hand side of equation 1 is right here. It's the derivative. Let's look at the right-hand side of equation 1. We've got negative 1/5. We said x1 is this function. So negative 1/5 times e to the negative t over 10 plus 80 plus 1/20th of x2. x2 we said is this function, 2e to the negative t over 10 plus 80 plus 12. So this is the right-hand side of equation 1. We're hoping that it simplifies to dx1 dt, which is negative 1/10 e to the negative t over 10. Well, how many e to the t over 10s do we have? We've got negative 1/5 of them. 2/20ths is 1/10. So minus 1/5 plus 1/10 e to the negative t over 10. And then what's our constant? Minus 1/5 of 80. Let's see, minus 1/10 of 80 would be minus 8. Minus 1/5 is twice that, so minus 16. Plus 1/20th of 80 is 4 plus 12. 16 minus 16 is 0, so that goes away. And we're left with minus 1/5 plus 1/10, which is minus 1/10 e to the negative t over 10, which is exactly what we wanted. So the right-hand side of equation 1 equals the left-hand side. So that's minus 1/10 e to the negative t over 10. All right, so looks like we have a solution to the first equation, but to be a solution of the system of differential equations, it has to satisfy the second equation also. So let's verify that the second equation, left-hand side, is this derivative here, minus 1/5 e to the negative t over 10. Let's verify that the right-hand side is equal to that. So the right-hand side of equation 2. We've got 1/5 x1, so I've already written that there. 1/5 of e to the negative t over 10 plus 80, minus 1/5 of x2, minus 1/5, and I already wrote x2 in there because that's 2e to the negative t over 10 plus 80. And then there's no plus 12 in equation 2. So here is the right-hand side, and let's see what this simplifies to. We look at e to the negative t over 10, we've got 1/5 of them here, minus 2/5 e to the negative t over 10, and then 1/5 of 80 minus 1/5 of 80 is 0. So this turns out to be 1/5 minus 2/5 is negative 1/5 e to the negative t over 10. Which is what we wanted, because dx2 dt is negative 1/5 e to the negative t over 10. So it looks like our solutions satisfy that second equation also. Therefore, x1, x2 given by these two functions is indeed a solution of the linear system of differential equations given here. The end.